July 1965. The air war in Southeast Asia is heating up, and a U.S. aircraft falls victim to a deadly new weapon. The first combat test of anti-radar missiles came with the war in Southeast Asia. Radar-directed guns had become a significant threat to strike aircraft. But more ominous still was the proliferation of radar-directed surface-to-air missiles, SAMs.
The SA-2 was a brand new device, a guided missile that the enemy could track while scan, and he could track several targets at one time, and he could shoot this missile, which is a flying telephone pole, 36 feet long and 3 feet in diameter. Looks awfully big, and it comes straight at you. The SAM did not hit very many airplanes, but it caused a tremendous amount of launches, or losses, I should say, because you'd have to go down into that small arms fire to evade the missile. So guns got most of the airplanes, although it was a SAM that made them get down where the guns could get them. So we had a very powerful combination with the Weasel, with Shrikes, and getting that 2-minute hold of silence so they could dive bomb.
That hole in the electronic maelstrom was created by the launch of a Shrike. The first operational anti-radar missile was introduced to the fleet in 1965. The Shrike, designated AGM-45, equipped Navy Iron Hand and Air Force Wild Weasel missions.
In the 64 timeframe, we really had nothing to counter a surface-to-air missile threat or a fire control radar threat.
As Shrike became available to the operators, the new radar seeker was used to cover alpha strikes, road sweeps, interdictions, any operation in which electronic defenses might be encountered.
By the time we got into the action with the Shrike was specifically a defensive suppression weapon. Our purpose in life was to keep the SAMs and the SAM radars actually off the air, and therefore if their radar was not on the air, they weren't going to launch against you. If they did launch against you, their weapon would go stupid because we would force them to shut down.
And as the electronic threat environment thickened with signals, the anti-radar missile became an essential tool.
So you had to sort of pick and choose what was really your threat. And then you had oral tones in your headsets. So you're listening to your GCI, your early warning radars, which would be a sweep that you'd hear back and forth. You'd hear your fire control radars, which would be sort of like a buzz, and then you'd hear your SAM radars, you would hear a definite chirp that would be a low chirp, low warble, we always call it, and then you'd go to high warble, which meant that they were locked and were tracking, and then you'd get another tone, which would be a deedle, 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 is the best way that I can describe it, and your big red light that would say launch. And that would mean that they were now sending commands to a missile that was after somebody. So from an Iron Hand perspective, you would try to locate the site based upon, first you'd have APR 25, 27 warnings, and then you would have your Shrike selected, and you would have your SIDS needles, so your needles which would indicate where either fire control radar or SAM was illuminating from.
My introduction to armed weapons was in Vietnam, and it was the Shrike. And that was all we had for the longest period of time, and the only weapon that could be carried on the tactical aircraft that I flew. And we learned that the Shrikes were very valuable in those days and could not be wasted.
Just as valuable, China Lake had sent its engineers and technicians out with the missile, out to the ships on Yankee Station, out to the bases where the war was being fought.
I knew Jerry Schieffer, and I'd seen him on board the ships in those early days, but I never realized he was from China Lake, or any of that information was being fed back into the RDT&E community. But I'm positive that it must have been because as a new threat emerged, there were changes made to the Shrike.
New tactics and new targets called for new Shrikes.
Remember, we started out with classic Soviet tactics, and then we evolved into a different situation because we'd never faced this kind of an enemy this well armed with these kind of sophisticated electronics. And that's what, bred the Wild Weasel program. It was a quick reaction capability to reduce the losses which we were encountering.
You could roll in, you could line up your needles, and then you had what was the dip angle. Okay, how far below the horizon did you have to dip in order to get your needles lined up? That was one way to shoot it. And it was a manual type delivery, and you had to sort of calculate in your head your dip angle and what your pull-up was so that you could get a little bit of a loft on the missile. To be real honest with you, you pulled until you felt it was about right and then pickle it off.
Pulling the nose of the airplane up 45 degrees and lobbing it, tossing it like a basketball into a basket. And sure enough, all that was free distance. Then it would still seek it out, and that allowed us to outgun them. We could shoot farther than they could.
The second method, which was probably utilized the most, was down the throat. So you centered your needles and you just fired. Typically, the sights would not be of any great distance away, so if you just centered the needles and shot, you're probably going to be pretty accurate.
We devised a tactic that we called the pinwheel, where every 15 seconds a weasel would go up and fire a Shrike, 2, 3, 4, go around and do it again, and we'd shoot them up to 30, 35,000 feet, and the Shrike would come down through the bombing airplanes, and we never hit one. It's a huge sky, but it did keep the gunners' heads down for that critical 2 minutes. And that's when the loss rate went way down, and Ralph, in his interpretation of CSAMs, permitted us to finish without being killed or captured.
The missile and its employment evolved in direct response to the lessons learned in combat. And the laboratory continued to deliver new versions to the fleet throughout the conflict. Shrike's early success made the enemy wary. Even the threat of an inbound arm was often good enough to accomplish the mission.
It was a very distinctive maneuver, this dip check. Was you would do this maneuver, and when you actually launched the missile, you would call over the radio so folks knew what missile was in the air, shotgun, and that was the call for a Shrike in the air. Well, the enemy operators soon detected this distinctive maneuver that the aircraft were making, and if they heard shotgun, they would shut down. Well, in the evolution of tactics and counter-tactics, as they began to shut down, even before we launched the missile in that, we had a counter tactic that we could actually go out without a Shrike aboard. We would actually go through the dip maneuver, shout shotgun, and in some cases launch a Zuni missile, which was substantially cheaper than the Shrike were, and they would shut down. So we had achieved our objective of suppressing them at the time.
And that worked for a short period of time until North Vietnamese aren't any dumb guys. They know a Zuni travels much faster than a Shrike. And they actually were able to discern the difference between a Zuni and a Shrike. So if you call shotgun and pickle off a Zuni, then guess what? They continued to radiate. So it was a little game of cat and mouse. So it got to the point of, well, we have to shoot a Shrike every once in a while just to keep them honest and get them to shut down. So.
Over the course of the Vietnam War, Shrike would become the most fired air-launched guided missile in history.
And whatever it took to get them to shut down was what we were after, because it gave the strike flight enough time to get in, drop their bombs, and get out of there. Of course, the ultimate answer was to destroy the site so that we didn't have to bother with them the next day.
And although the controversy over defense suppression versus hard kill would linger, no doubt remained as to the future of arms in combat.
By the time Vietnam was over, there was no question, after firing some 10,000 Shrikes there and many standard arms, we've talked to pilot after pilot that became a real believer in arms. Right now, it's just it's not questioned as to the fact that an arm is a necessary part of our weapons arsenal.
The true measure of a weapon of this nature is not really so much its terminal effectiveness as it is to the survivability of the strike force. It's a deterrent weapon. Ideally, if it were 100% effective, you'd never have to use it. Because if the radars stay shut down, then they pose no problem to the strike force, which is the principal objective for the missile to start with.
One sees the introduction of new weapons and then a response, an anti-weapon. And this is one of the oldest themes in military history of response and counteraction and response and counteraction.
One of the immediate responses to this new technology was chaff. Codenamed Window, strips and flakes of metal were dropped from aircraft by the bushel load to reflect enemy radar signals into all the wrong directions. Chaff helped. Early attempts at active jamming helped. But as radar improved countermeasures were required.
On the defensive side, you've got chaff and radar warning receivers and individual systems on aircraft to spoof or block the capability of an emitter and a target system to track you. And by the way, that also includes stealth as a tactic. But again, as you get, you can't defeat the laws of physics, and as you get very close to radars and the missiles that they are responsible for guiding, it becomes very difficult to put enough power or enough stealth in an aircraft, and at some point you have to put something lethal on the target.
The first attempt at destructive countermeasures for radar was the Moth missile, developed by the National Bureau of Standards and Harvard Research Lab.
The Moth was a missile devised during World War II to work against German AAA guns that were defending Germany against the raids that the Allies were then conducting against the German cities and German airfields, etc., from Great Britain. The idea was to knock out the radars that were then being used by the Germans to alert the AAA guns and to help target them.
With the war nearing its end, the Moth project was abandoned before deployment, but it set a precedent that would not soon be forgotten. Radar was, indeed, one of the wonder weapons of the Second World War, but the Korean conflict quickly illustrated just how powerful a weapon it had become.
One of the key developments was the use of Russian radar directing devices for their anti-aircraft weapons. And it became such a threat that in the latter stages of the war, for example, there were restrictions on low-level attacks. A lot of our aircraft were being hit. A lot of them were being shot down. And to a large extent, that results from radar direction of anti-aircraft weapons, anti-aircraft guns in this case, by the North Koreans and the Chinese. So unlike World War II, the United States faced in the Korean campaign radar being used by the enemy in an offensive fashion, if you will, in a highly effective fashion. And it was obvious that we needed to go after the mine that directed those weapons, those anti-aircraft weapons, the radar set, as well as the guns themselves.
Guided missiles were still in their infancy, but American ingenuity and the Navy lab at Corona responded rapidly to the new threat environment.
The second arm would be the BAT-2. That's the missile shown over here. It was a BAT converted to an anti-radiation missile. This work on this was done during the Korean War. So the idea was to knock out some of these radars that were, at that time, gunfire-directed radars in North Korea with the BAT missile.
Corona's innovative approaches to arm design allowed the BAT-2 program to become BAT-Corvus and eventually evolve Seeker first into Corvus, a large and complex multi-mission missile and a product of the Cold War 50s. The eventual Corvus was envisioned for both tactical and strategic use.
Now, it could knock out an airfield by hitting the radar that was at the airfield because it carried a nuclear warhead. And of course, getting a nuclear warhead anywhere near the airfield knocked that one out. It was a successful missile in that it flew from 160 miles out, I believe, in actual flight, and had 20-foot miss. And when you had a nuclear warhead, you didn't worry about such things as that. But the problem with Corvus was the cost.
Cost aside, Corvus beat out several competing Air Force programs to become the Joint Service Arm. However, a contemporary development at China Lake would lead directly to Corvus' most serious competitor, the Shrike. In 1954, as part of an effort to investigate advanced air-to-air missile technologies applicable to the new Sidewinder missile, Knotts demonstrated a passive RF seeker, one that homes on radar emissions, with a 5-inch Sidewinder airframe. An elegantly simple crystal video device, this experimental missile seeker would set the stage for an entirely new development program. The development of Shrike began unofficially in the summer of 1956, when the CNO issued an operational requirement for a small, tactical anti-radar missile system, and when the threat was becoming ever more immediate.
And Shrike was an entirely different type of beast than Corvus. It was much smaller, much cheaper, keyed to defensive radars that were coming into play in those days. And about the time of the demise of Corvus, in the latter days of Corvus, was when it became very apparent that the SA-2s were coming into wide use then.
Commander Bill Moran had returned to China Lake at about the same time, and he had returned with the experience of the North Korean guns fresh in his mind.
He asked the question when he was here as a technical officer, can we build a missile that would go after radars? And Leroy Riggs was involved. Leroy was involved in some of the paperwork that went from the center to Washington saying, hey, we think we might be able to build an anti-radiation missile. And then he was back in Washington and he helped answer some of that paperwork that he had sent to Washington. But anyway, they sold the idea of we got some money to see what we could do, and we built 2 missiles and fired 2 missiles, and one of the 2 worked.
Knotts sold the feasibility study, but, as had been the case with Sidewinder a few years earlier, the project was not universally supported.
The notion of a radar homing missile got into the works, again with some real confusion in terms of what the Washington scene said the requirements really were. And once again, you had a set of folks saying there is no requirement for such a device. That's hard for some of the attack pilots of today to understand that anybody ever made such a statement, but that's the way that worked.
Nonetheless, In September 1958, the Bureau of Ordnance tasked Knotts to determine the feasibility of a new type of anti-radar missile. Knotts China Lake's feasibility study took into account the radar threat and the technology available for the development of anti-radar missiles. NOL Corona conducted fusing studies, and in 1959, Cobra was presented to the Bureau.
The Naval Ordnance Test Station has recently completed a feasibility study of a simple, reliable, inexpensive weapon. The primary goal was to provide an offensive capability against radar systems as they may be employed within the limited war concept.
The ARM feasibility study had included fabricating several missiles that combined a number of available technologies and hardware.
Since it looked like the program was coming on to be a solid engineering development program, we attached a name to it then, and the name at that time was Cobra. We took a couple of Corvus seekers and a Sidewinder hot gas control system, mounted it into this 8-inch airframe, and as I recall, the first motors we used, we strapped together 4 2.75-inch rocket motors together in a bundle, and that was the first motor. That first firing was a miserable failure for probably any number of reasons, but we sure learned a lot off of that. The next one we put together, and it looked to me like the plane had fired it directly at us. And I and myself and others were nervously looking around to see where we could jump off of the roof of the building, and then we could start hearing the thing coming in. And we were beginning to get a little scared when all of a sudden out in front, right by the radar, a big splash of dust came up. And the thing had successfully guided, and we were just absolutely overjoyed that that test was successful.
This is one of our armed test vehicles. It is passive, receiving its signal directly from its target S-band radars.
Cobra already looked a great deal like Shrike, but considerable technological evolution would be required to make the shift from snake to bird.
Will cost about $4,000 each in mass production.
The ARM feasibility study yielded Cobra, which by 1961 had been renamed Shrike, for a small bird that folklore had it pecked the eyes out of its enemy. And by 1961, the development of Shrike was in full swing.
Now, the fact that that was successful allowed us to make enough hay off of that to where we went back, got some funding to where we could come back and do the job right, because we saw all kinds of problems in trying to approach the task that we were doing. Using that Corvus guidance system was a monstrosity. A lot of problems in the servo. We had to get going on the design of a warhead and fusing system. We had to come up with a better rocket motor, solve some of the airframe problems. Joe Mosco arrived on the scene then. They redesigned the control system, again based on the hot gas servo from Sidewinder. Took a Sparrow motor, which was 8 inches in diameter, and used it directly. Got fusing work started at the Naval Ordnance Lab at Corona. They had some very good ideas there. I believe Paul Cordell was the primary engineer on the warhead. They had a fuse warhead combination idea that was just outstanding, where the warhead had something like 22,000 3/16-inch steel cubes surrounding the explosive. When that went off, it went out in a fan beam at about a 70-degree angle, The fusing was set to detect when it passed the antenna at 70 degrees, and that combination was very potent against an antenna.
For the design team, providing simple, elegant solutions to complex technical issues remained paramount. Shrike was essentially a ballistic rocket with terminal homing.
We decided to do an anti-radiation missile in exactly that concept. Let's see if we can't let physics work for us instead of working too hard.
And right from the beginning, we were concerned about having a simple, low-cost missile. And for example, there were influences that said we ought to put the antenna on a gimbal. And we worked real hard to keep the antenna fixed to the body so that there would not be any moving parts, because that would reduce the cost.
But the Seeker remained a challenge. China Lake put together a highly talented team to push the state-of-the-art to meet that challenge.
The first two anti-radiation missiles that were fired here at the center did utilize the Corvus antenna system. The remainder of the Seeker was pretty much built here in-house, and following those first two firings, the complete system was built entirely here at China Lake.
Most of the technology at that time that was needed to build Shrike was in the front end, in the guidance unit. As I say, a lot of the remainder of the system, the control section, rocket motor, wings and fins and so forth, they used as much as possible things that were pretty much off the shelf. There wasn't a lot of technology around at the time in terms of broadband tracking systems. And broadband back then was like 20% bandwidth.
Nobody had ever tried to build anything that complex in that small a space either.
The technology that really made that possible is what today I guess you could call a strip line or microstrip. You have a dielectric, which is kind of the gray or blue in here, with a conductor over it and a conductor underneath it. And it permitted Corazine, Moscow, and that group to design antennas that were much, much smaller than waveguide. So from the antenna RF processing area, without question, that's the technology that made that possible. But technology was just part of the equation. The larger part was what those guys did with it.
What the China Lake team did was exploit emerging technologies that allowed novel antenna and RF signal processing designs.
At the time we started Shrike, we felt that this newfangled system of microwave transmission lines called strip lines would be our ticket. I think that decision was less dramatic than when we made the decision to that our baseline approach for Shrike would not be a cluster of 4 helical antennas or spiral antennas, but that we would use a single broadband spiral for doing the monopulse function. We demonstrated that we could synthesize, design, construct, and build fairly quality couplers and phase shifters over 5-to-1 bandwidths or greater. Having that design skill here, of course, made it possible for us to, in a serious way, going out and actually implementing broadband monopulse networks.
The 4-arm spiral antenna, integrated with RF signal processing implemented in strip line and a solid-state guidance computer optimized for compact, rugged simplicity, made Shrike a unique prospect. As Shrike's guidance section was evolving, it became clear that innovative approaches to the ordnance section would be needed as well. China Lake's well-established expertise in energetic materials, warhead design, and propulsion came to the fore.
We came up with a unique warhead for Shrike, Paul Cordell and some of the other people out in the warhead group.
The missile has a number of variables that lend itself to a particular warhead design. We had determined that fairly early in the study.
Part of the challenge was delivering a relatively small warhead with a variety of potential angles of approach onto a target that could be quite complex.
We evolved a design for a variable charge to mass ratio warhead. And that warhead then will project its fragments at different velocities. And in order to model this on the computer, we essentially broke the warhead into 5 different pieces. We had 5 different charge to mass ratios, and we could determine then from well-accepted fragment acceleration formulae what the initial velocity of the fragmentation would be, and then we could determine from tests how much variation in that velocity there would be in each fragmentation beam. So we optimized the fragment size around the ability to penetrate what was left that you could not protect and still have a functional radar system.
The new Shrike warhead was also designed to employ new explosives to propel its 22,000 preformed fragments, another area in which China Lake was a pioneer.
So we selected a new explosive material, the first of the castable PBXs, which are more temperature tolerant than a TNT-based explosive would have been. And it turns out that it was a good selection, and it does retain the effectiveness of the warhead to the extent that we desire.
And the warhead was designed to be a tremendous shotgun with pellets that would penetrate light metal and go inside and ruin cables and things like that. All we wanted to do is to take the radar out of the action.
A highly effective warhead and a high-tech guidance system still wouldn't get the missile to the target. The feasibility rocket motor was unsuited to the mission, so an off-the-shelf candidate was selected.
The concept for Shrike originally included modifying the Sparrow rocket motor, the Mark 38 that was in development at Rocketdyne, McGregor, Texas. And with slight modification, it became the Shrike propulsion system. There was nothing 8 inches in diameter and of reasonable performance capability available but that Sparrow motor.
That early motor was problematic. It was complex and expensive, which did not fit with the program's design philosophy.
The Sparrow motor was a very difficult design to build. So we were constantly having to fight ballistic anomalies, we called them, rather than failures, because the additional grain surface that got exposed would give a pressure spike, not necessarily blow up the motor, but certainly make one apprehensive. The other problem that we had with that was it was very labor intensive to build. And so those rocket motors in the initial production were costing $10,000 a piece in 1960, $2 or $3.
A new propulsion system was quickly put into the works. China Lake's performance specs resulted in the Mark 52-53 motor for Sparrow and Shrike. The new motor was far more reliable and far less expensive. And competition with the new Mark 39 motor brought the price of propulsion even lower.
We were able, over the course of probably 10 years, to put out competing bids and get the Aerojet and Rocketdyne folks butting heads on every procurement. And as I recall, the price dropped down below $1,000 for Shrike rocket motors at the peak of that competition.
The Shrike team decided to follow on with a dual thrust or boost sustain motor for better range. resulting in the development of the Mark 78. The Mark 78 motor had an unexpected advantage, one which would influence the future of arms and other tactical weapons under development.
It also had no smoke generated because there was no aluminum powder in it as a fuel. After this version of Shrike was in the fleet for a while, the Navy decided we really like that, no smoke in the sustain, because we were having problems in Vietnam with visual cueing of the radar operators seeing the missile in flight and seeing its smoke trail and shutting down the radar. So the outcome of that was that the OpNav folks established an operational requirement that any future arm weapons be smokeless. Now, it's physically impossible to make something that's totally smokeless and still have significant amount of energy. But we were able, using advanced technology, to come up with propellants that were of reasonable energy, slightly reduced performance, but still reasonable energy, and no smoke unless the humidity was very high. And that's what we then called reduced smoke propellants, because smokeless was really not achievable.
The first deployed arm was also the first deployed missile with a reduced smoke motor.
In some of the early testing, I can recall a Navy pickup being driven down the G1 range road at
I remember that.
At 55, 60 miles an hour, with a arm out the window with a scale model of the Shrike on the end of it in order to determine aerodynamic information.
While the missile was being developed and refined, the China Lake team was also developing and refining testing techniques to meet the unique requirements of anti-radar missiles. China Lake created a complete threat environment for evaluating arm hardware. And Shrike testing demanded an odd combination of supersonic tracks, aircraft racks, and other specialized test platforms.
We would take a crew of about 8 out with us, and it was always very early in the morning. And the reason we went to the hot air balloon was we tried a helicopter. We had too much glint off the blades of the helicopter. We couldn't set over the target, which was in those days an SCR 584 radar located at Charlie Range. And so this way we could tether, and we would be 500 to 1,000 feet above the ground, and we could sit there. We had the guidance section only hanging out over the side. We had RF absorbent on the side to keep any reflection coming off the metal, and we could rotate the antennas of the target. We could point it straight at in the main beam. We could pull it in with the tethered vehicle. We could go out away. We could come down low to get close to the ground for ground reflection, and it worked out very good.
The balloon-borne test program was a highly effective and extensively utilized adjunct to the simulation and hardware test assets at China Lake.
We had an A4 aircraft instrumented, what we called nosy, which the guidance section was in the nose of the aircraft, but again, an A4 aircraft in those days don't stop like a helicopter. So with this, we could stop in midpoint and get data point, move in a little closer, get another data point, move in a little closer, and get another data point.
But there was still no substitute for live firings. Early in the program, Shrike faced a new challenge. This one from a sister service with a modified bullpup called GAM-83.
We had a head-to-head competition with the Air Force, and this is competition between the Navy and the Air Force, and we won that competition because we were further along. The Air Force described that the toughest situation would be 2 targets 100 feet apart and having a missile which could guide and hit one of the targets, and they described that as the toughest situation. So between a couple of meetings, we went out and fired a Shrike at 2 missiles, or 2 targets that were 100 feet apart, and we impacted 10 or 15 feet from one target and took the data back and said, that's not a problem, we've already demonstrated it.
The biggest challenge for the early development program, however, came in the wake of the discovery of Soviet nuclear missiles in Cuba in October 1962.
Probably the most exciting and excruciating part of the Shrike program, something which was highly classified at the time, was we built a developmental model seeker here at the center, and we actually packaged one of those in an aerodynamic shape, put it on an A4, and we flew it down to Cuba and actually received the signals from the advanced SAMs. And as soon as we basically confirmed that they were there, we were put into the EASY program, which is Emergency Shrike Effort Program.
The EASY program to make pre-production missiles available to cover a possible invasion was taken on at presidential order.
I built the first 24 RF seekers myself on the bench, and we built the first 100 missiles here on the center, the complete missile. It was a combination of a brand new seeker. We had a Sidewinder gas grain generator that we used in the control section to power up the control section. We developed the warhead for it, which was 22,000 fragments, and put them all together right here, and we're ready to go.
The president got to see Shrike for himself the following spring when he visited China Lake.
The target was so far downrange that they had no way of knowing whether it hit the target. We didn't hit the target, but the president didn't know that, as I recall. We had all the different weapons that we had worked on lined up on both sides of the parking lot, and I had the privilege of standing by the Shrike weapon, which was on display.
A key element of the Shrike story was the application of engineering disciplines by an in-house laboratory team that kept the program on track.
Throughout the program, the government took responsibility for the system. It was not something that we passed off to the contractor in exchange for a large lump sum fee and a promise to deliver a total package at a future date. Throughout the life of the program, it was China Lake that took responsibility for it.
Even before Shrike's combat debut, production problems had threatened the availability of arms to the fleet. The laboratory team scrambled to establish a second production source and get missiles to the operators in combat. The engineering discipline developed at China Lake through in-house development programs allowed the station to take a direct approach.
We certainly were able to keep the documentation under control, as indicated by the second source. We're able to get second sources into the business quicker. The government has a better record of what it is that they're producing. They maintain the control. And as a result, that whenever you have technical problems, you always have an in-house team that is available to go and solve these, where if you have to depend upon industry, you may not get the same kind of response or service.
The second source didn't have the technology that TI had, and all he had was the prints, and so he religiously designed them to the prints, brought them out here and fired them, and they worked just exactly the way they're advertised. And of course, then that put the pressure back on TI, and NAVAIR got us back in the loop as far as monitoring the changes and providing production support. and then TI's hardware came up to good quality.
When you have a good documentation package, build to it and test to it.
It was a very competitive situation, and the cost actually went down over time. Well, it should have gone down because of learning curve and increased quantities, but it would not have gone down, we believe, as much as it did if we hadn't had the competition.
Shrike entered Navy service in 1965. Original versions of the weapon were fielded as soon as they became available to provide a basic capability. Dash 1s and 2s went after old fire can radars and the ubiquitous Fansong family. By 1966, they were being replaced by the new Dash 3. The Dash 3 was the real workhorse of the conflict, with some 16,000 units produced in 3 versions, including one targeted for Barlock early warning radars. The Dash 3 introduced angle gating, significantly improving missile lethality.
So what we had to do is build electronic gates in the control loops to say, okay, this is the guy we want. This is the guy we're locked onto. Anything outside within plus or minus 4 degrees, which is what our design was at the time, plus or minus 4 mechanical degrees, I'm tracking this guy, the missile turns around, okay, so I'm heading maybe to this guy. This guy comes on, that guy comes on, that guy comes on. As long as they're more than plus or minus 4 degrees outside of our electrical track angle, we won't see them.
As new technology came available, and as new threats emerged, new Shrikes followed, incorporating broader bandwidth and covering more radar targets.
There were several attempts to widen the bandwidth of the Shrikes. As the war went on and the other side developed more radars at different frequencies, some of the frequencies were outside of the original bands that we had Shrikes, and as we developed more Shrike heads to meet those particular threats, aircraft couldn't always carry all the right versions of Shrike, and we developed the Dash 9 and Dash 10 to basically cover the whole frequency band range of the targets that were around in that time frame.
Dash 4, Dash 5, Dash 6, and Dash 7 Shrikes were developed to suppress headlights, low blow, flat face, and new generations of Fansong.
To support the increased combat activity in Southeast Asia, the Navy laboratory community was tasked with a number of quick response programs.
During the latter years of the war, and almost exactly a decade after Easy, Shrike was again the focus of an emergency quick response effort. 104 days after program initiation, Shrike on Board, the SOB, was successfully used in combat. SOB provided a ship-launched defensive capability against enemy shore batteries. By the end of the war, more Shrikes had been fired in combat by the U.S. than any other guided missile.
We've fired close to 9,000 of them in combat. We fired over 1,000 of them here on our China Lake ranges. We had any and every kind of firing.
The further development of arms did not stagnate with the success of Shrike in Southeast Asia. Other activities and industry, notably the Naval Ordnance Lab Corona, pursued armed technology and modifications for existing systems. Bullpup, Condor, Sparrow, Talos, and even Polaris were studied, and in some cases modified and launched with anti-radar guidance. The only modified missile to see significant operational employment was an ARM version of the surface-launched Standard missile. It also saw some sibling rivalry.
At that time, Standard Arm was being pushed by Corona, and we considered it a competitor to Shrike, and not a very good competitor, something that would cost 10 times as much and not perform much better than Shrike. And so we had lots of discussions, which at times were not too friendly with our sister lab at Corona, about the virtues of Shrike versus Standard missile.
You might view Standard Arm as a version of Shrike in one way, And the reason it was called Standard Arm, they took the basic Standard missile and put an arm seeker on the front end. Turns out the arm seeker they put on was a Shrike seeker.
Standard Arm was fast and highly competent. But also large, cumbersome, and highly expensive.
I think the Navy developed the Standard Arm, that's my recollection anyway. We had this missile, but it was so expensive, I think they only got to shoot 6 in the whole time we were over there, and I don't remember who got to shoot them. It certainly wasn't the Weasels. And so, back to, I guess, the political or the economic part of war, if we hadn't had a Shrike, which was cheap enough that we could burn a whole bunch, we would have never been able to develop this tactic because we couldn't afford to shoot Standard Arms like that.
Standard Arms limitations left Shrike as the premier defense suppression tool. Shrike's limitations, too, had been duly noted, and the development of its successor had been initiated. Shrike 73 was started during the height of the Vietnam War to provide the fleet with the high-speed anti-radiation missile it needed for the battlefield of the 1970s and beyond. U.S. allies had also noted Shrike's utility in Vietnam, and the missile was soon in combat as far afield as the Middle East and the South Atlantic.
The Israelis had used Shrikes in both of their wars very effectively, and they had even done some modifications of Shrikes on their own where they could ground launch them as well as launch them from aircraft. But I would guess that they probably fired over 500. The Brits in the Falklands, I know they fired off their Vulcan bomber.
The later model Shrikes were carried all around the world throughout the 1970s and well into the 80s. The last hurrah for the AGM-45 came during Desert Storm, when limited numbers of the aging missile were fired by Marine Corps and Air Force units. By the end of the decade, nearly all remaining Shrike assets had been taken out of service, demilitarized.
What we wanted to do was to maintain the philosophy of the simplest, least expensive missile we could come up with, which would do the job. And so the name Shrike 73 was a good name.
Shrike 73, an in-house program, run like Shrike had been, to create the next generation arm. That's the way it began.
And I think it was 1968 and 69 that I actually put about $600,000 of my cost center overhead for 68 and 69 into work on harm. And that's basically how it got started.
By the time we proposed Shrike 73 or harm, the technology had advanced to the point where we could, in one antenna seeker system, we could build a guidance system that would replace all of the versions of Shrike. And that advance in technology was due to the fact that we had had erased funding, and we had had people like Moscow and Corzine and their technical support team advance the technology.
Stripline opened the door. The forearm spiral put a block in the door so it couldn't shut. Our guys saw the importance of it and charged. And that's what gave us the broad RF bandwidth we have today. The designers who designed this guy, to my knowledge, is not an anti-radiation seeker, modern anti-radiation seeker in the free world that doesn't use this technology.
The technology for advanced arms had been developed and refined under a broad program for electromagnetic radiating source elimination, ERASE. ERASE was an outgrowth of laboratory efforts during the 1960s to increase Shrike's bandwidth.
But it's really been the ERASE program, I feel, more than any other single item that has resulted in a lot of the performance improvements in armed weapons that we've had today. The ERASE program has had the luxury of being able to work on things that are high risk and without pressing development schedules. We've been able to evolve new components. A great deal of the antenna and RF technology that we have today that go into both, well, for that matter, Shrike, Standard Arm, and HARM has been an outgrowth of the ERASE efforts.
And we wouldn't have HARM, we wouldn't have Standard Arm, we wouldn't have the APS 117 TIAS, systems of that sort had we not had this basic technology program. And Corzine and crew were able to put together a HARM seeker because of the ERASE program.
Many of the design people that had been involved with Shrike and the ERASE program were involved in putting together the first HARM, what turned out to be the HARM missiles, to prove these new concepts. Those missiles were fabricated, checked out, fired on the range, outstanding success there. The second or third one, I forgot which, went just about square through the center of the antenna. We had learned how to make the much more accurate guidance than we had with the Shrike fixed body system, how to compensate for some of the errors.
HARM also had similar ballistics to Shrike's, but with the refinements that technology allowed.
With the Shrike, you had to do a bore sight maneuver to do the triangulation to get the range of an emitter. You'd actually dip the airplane to put the bore sight of the Shrike missile on the emitting target, and then depending on your altitude and that dip angle, we called it at the time, you calculated the pitch up angle that you had to pull the aircraft to launch the missile in order to get it to the range where the target was. In HARM's case, it actually did that maneuver on its own after it left the aircraft.
The ordnance sections, too, were direct descendants of Shrike.
The original HARM firings actually had an 8-inch diameter reduced smoke rocket motor stuffed inside the 10-inch airframe. And we took that technology and designed and built the first 2 HARM rocket motors here at China Lake to show the capability that could be used for HARM.
HARM is a quantum leap as far as the modes in which you can shoot it, its ability to discriminate between targets, the interrelationship with that and the EW systems that feed into it. There are many, many vast improvements in the weapon itself, but I think there's also a vast improvement in the interface and with the capabilities of the weapon systems that are resident in the aircraft.
Before HARM could make that quantum leap, however, the program had to get past some rather dramatic changes in the Navy R&D environment.
HARM is a good systems acquisition program to study because it had every possible mistake made at least once.
HARM probably is the best example of how not to do something.
Now, the HARM program has been in political football all the way through, at every level of government. I've never seen a program in my whole career that has had so much attention by so many people and has been redirected or had money stopped, whatever.
It started as an in-house development, and we had planned a rough count of 100 technical people that would be involved here at the center, just as they were in Shrike, just as they were in Sidewinder, just as they were in every successful weapon that had made China Lake famous. And in the fall of '74, when the contract for development of HARM came to the center, and it included the center doing a lot of the technical work, but including a contractor very significantly. We had learned our lesson, get the contractor in early, but you better know more than he does at all times, technically, about the job. And that was the plan.
That Navy industry team effort was not to be. The technical team was deleted. In-house participation was marginalized, distancing the program from both the laboratory and the fleet.
And it took a long time to get harm out, and the price just kept escalating on the thing.
I think that we would have had something in the fleet in about the 77 time frame had we continued right on in-house. It's maybe 78 at the latest.
Harm was released to the fleet on the A-7 aircraft in 1983. Redirections, delays, overruns, and poor technical decisions in headquarters aside, Harm made it to the fleet, and eventually made a respectable name in combat. Harm made it back to the lake, too. The laboratory team would work with the contractor to integrate advanced guidance with advanced propulsion and warhead and fuse, and to mate the missile with its aircraft. More complex to integrate than Shrike with its minimal avionics, Harm nonetheless was adapted to a variety of platforms. And as new and more potent technologies came available, Harm evolved to meet new and more potent threats. Part of that evolution was a politically plagued outfall of China Lake's ARM technology program.
So the low-cost seeker was trying to bring things that they had learned from the erase program, make it simpler to build, using less expensive components, infusing the new technology, improvements on packaging and so forth. Unfortunately, it came too late in the program to really realize the advantages. You were already down on the learning curve on building harms. It was pretty hard to get enough money to do the development, get it productionized and whatever. When somebody is already in production on a multi-million-dollar, i.e. billion-dollar program, you're going to run into politics.
Although low-cost seeker was never fielded, the laboratory and the contractor did find their way to a productive relationship. Certainly less controversial was sidearm. Erase technology derived from the canceled anti-radiation projectile project was applied to a 60s vintage Sidewinder AIM-9C to create a small, effective anti-radar missile. Sidearm saw limited use in Desert Storm and remained in the Marine Corps inventory for another decade. Other arms have been pursued, under strange names and super-secret programs. But, 20 years on, Harm is the mainstay of the U.S. arm capability. Like Shrike, it has been adopted by numerous allies, and like Shrike, it is a frontline necessity.
As long as there are surface threats on the ground shooting at airplanes in the sky, ARM will be in the air.
The arms have always been used for specific suppression of specific radars, and the more lethal the radar was, the more you'd be likely to assign an arm to it. And as missile defense ranges, the ones that they're shooting against us, have grown, there's a need for greater standoff, both from the active jammers and the anti-radiation missiles. That's where Harm was an advantage, and the next follow-on systems in terms of anti-radiation missiles are likely to have even greater range and speed.
Throughout the 1990s, in the laboratory and in industry, high-capacity, high-speed computer processors were combined with the RF technology derived from Erase and other programs to spawn a new generation of arm seekers. And with faster, more powerful, and even smart ordnance emerging, arms began evolving at an ever greater pace. And the transition from the suppression of enemy air defenses, SEAD or SEAD, to the assurance of their destruction is on the horizon.
Now that we have the technology and we realize folks have this shutdown and blinking and techniques that they use to avoid arms, is DEAD or DEED, destruction of enemy air defenses. And where we see arms going is a single system with both capabilities. There's always going to be a need to negate the enemy's counter-air defenses.
HARM has done an excellent job in suppressing the threat. What we are seeing now in the relative concept of SEED is let's go to DEED, which now instead of just suppressing, let's destroy. Because every time that we go on a mission, we lob a bunch of harms, create a sanctuary for a short time, but when we go back the next day, we have to go do the same thing all over. So we expend a lot of weapons. So we need to start thinking more in the concept of DEED. And from a fleet perspective, their drive is to make the weapon more effective, make it more lethal.
Evolution with some revolutionary additions. The new arms will be a synthesis of new and emerging technologies, network-linked weapons that provide their own battle damage assessment.
And that's where the follow-on to HARM is. So the follow-on to HARM being ARGM, or the retrofit to HARM being ARGM, is to take the technology of today and make the weapon, increase the weapon's lethality, and also bring in the net-centric enablers from receiving national information or information over a link to present that information to the aircrew in the cockpit to make a real-time decision on whether or not to engage a specific threat. And then another benefit of the follow-on to HARM is we'll have a weapons impact assessment transmitter. We're going to be able to send information about where the weapon impacted. What else the ARGM weapon will bring is the ability of the warfighter to be able to say, I want you to go to spot X, and I don't want you to leave spot X. That's called geospecificity. This is where I'll impact. The concept behind that, you'll reduce the possibility of being pulled off on an ambiguous threat. The beauty of that is we've proven that technology, that capability here at the lake in 2003 with the Quick Bolt program, where we actually took national information in flight, had it correlate with the threat on the ground, launched the weapon, had two systems out there. We shut down our primary system, the one that we were really targeting. The system tracked both, recognized one shut off, recognized another was still on. Just prior to impact, it'll send back a weapons impact assessment transmission, which it did through the national architecture, and we were able to determine exactly where it hit.
And as with Shrike over 4 decades before, ordnance sections are being tailored to the new mission.
There is a program on this base right now called HSAD, which is going to take a HARM missile body, take the rocket motor off, and put a ramjet engine on. And that program is going to help demonstrate, hey, if this works, we can then consider transitioning ARGMs with this new rocket engine, this ramjet engine. And what that does for the guys flying is as the threat evolves, their stick has become quite large. We are slowly transforming that system into a more lethal, more geospecific, and more interoperable system with the whole battlefield to transition that role from just SEED to DEED.
ARM has come a long way in the years since radar began its ascendancy on the field of battle. From a reused glide bomb to that borrowed seeker driven by a cluster of borrowed rocket motors that presaged Shrike. to a ramjet-powered, multi-mode seekered, satellite-linked automaton that provides its own BDA. The arm may not be the perfect weapon, but it remains the iron hand of the fleet.
Thank God for Shrike, and thank God that we've got engineers who can put their head down and figure out weapons and give them to us to do the job with. You can't always have an engineer tell you how to employ it, but if they do the design right, then by God, we'll figure out how to use it.
A shrike is a bird. Butcherbird is another name for it. Shrike is a bird about this high. Voracious killer, tends to eat everything it's killed, but when they kill something, a rodent, small rabbit, they like to hang it on a twig, hang it on a fence post, just hang it out there. You know, let it dry out, let it turn to jerky. And it turns out the way the shrike killed the animal is it hit it behind the neck, break their neck, and then take it, fly away, and stick it somewhere. Well, when I first got on shrike, I said, gee, where did shrike name came from? They said, well, a shrike is a bird that pecks the eyes out of its enemies. I said, cool, man. What a heck of a name. These are the eyes of her enemies, without question. What does shrike do? Stops them, picks her eyes out. Great name. Well, I did some research, and one, shrike doesn't have a beak for it. It's more of a curved beak than a pointed beak that would be used for pecking in impaling. It's more of a curve, pardon me, a curved beak to break bones, cervical vertebrae of their prey. Where the name came from, I have no idea. The name's here, we gotta live with it. But it's a real, as far as I can find out, it's a real misnomer. Somebody said, gee, a shrike picks the eyes out of its enemies, and it went from there.